Okay, today we're looking at lesson 2 and talking about theoretical probability and experimental probability. Now we know probability is the measure of how likely an event is to occur, and that probabilities are always expressed as percentages or as rational expressions of fraction, anywhere from 0 to 100%, or as a real number from 0 through 1. An outcome is each possible result of an experiment, and the sample space is all the possible outcomes. An event is a set of the outcomes or a subset of the sample space. When we're calculating theoretical probability, we want to take the number of favorable outcomes and divide it by the number of outcomes in the sample space. And a complement is the probability of something not occurring. So if I want the complement, I've got to say 1, which it would occur, and subtract the probability of the event. So the complement of an event is the set of all the outcomes in the sample space that are not in the event. And then we find experimental probability when we take the number of times the event occurs and divide it by the number of trials that we're going to perform. So let's jump right in here. If we're finding theoretical probability in a jar that contains 50 red marbles, 20 white marbles, and 30 blue marbles, and you're going to pick one marble from the jar at random, we want to find the theoretical probability that you're going to get a red marble. So if there's 50 red marbles and the jar has 50 plus 20 plus 30, so that's 100 marbles, then the probability of a red marble would be 50. That's our favorable outcomes divided by 100, which is our sample space. So that would be 1/2 of the time, or we could say 50% of the time. The probability of drawing a blue marble would be 30 out of 100, which is 3/10 or 30%. And the probability of not white, well, 20 of them are white, so 50 plus 30 would be 80 of them that aren't white. So that would be 4/5 or 80%. And the probability that you get a red or a blue, so red there's 50, blue there's 30, that would give us 80 for our favorable outcomes out of 100 possible in the sample space. 80 out of 100 again is 4/5 or 80% in that case. In example 2, each of the numbers 1 through 10 are drawn on a card and they're placed inside a bag. The bag is shaken and one card is drawn at random. We want to know what the sample space is. Well, the sample space would be all of the cards that are numbered 1 through 10. So we're listing our sample space as a set. And then part B, what is the event of drawing an odd number? So the event would be our favorable outcomes. A 1, a 3, a 5, and a 7 would be an odd number out of our sample set. Plus 9. Left off 9 here. 1, 3, 5, 7, and 9. And then what's the probability of drawing a number less than 5? Well, that would be drawing a 1, a 2, a 3, or a 4. So there are 4 favorable outcomes out of our 10 sample space, so that's 2/5 or 40%. And then what are the odds in favor of getting a number less than 5? So that would be 4 out of 6 or 2 out of 3. Then in example 3, there are 30 students in study hall. The table shows the number of students who are studying a foreign language. What's the probability that a randomly selected student is not studying a foreign language? Well, there are 14 plus 8 plus 5, so that's 27 students. There's 27 that study foreign languages. And there are 30 students in our study hall. So the probability of not studying a foreign language would be the 3 that are left over out of the total 30. So 27 are studying here, and the probability of not studying a foreign language would be 3 out of the 30, or 1 out of 10, or if you wanted to say 10%, all 3 of those would be correct. Then in example 4, we have a class of 150 students. 95 are taking math, 76 are taking science, and 53 are taking both math and science. One student is picked at random, and we want to find the following. So in part A, we want the probability that they're not taking math. So not taking math. 95 are taking math. So 150 minus 95 leaves us with 55 that are not taking math. And if you reduce that down, 55 out of the samples, out of the total number 150, that would reduce to 11 out of 30. And using my calculator, 11 divided by 30 is about 36.7%. On part B, the probability of taking neither would be 32. So 32 out of the 150 total is 16/75, and using our calculator, that's roughly 21.3%. Then on part C, the probability that you're taking math but not science, that would be this group here, math but not science. So 42 of 150 is 7 out of 25, and that is 28%. And it looks like in my Venn diagram over here, the math label was not showing up, so be sure to add that in your notes if it's not there. Now in example 5, we see students are given a 4-digit code for computer access. No digit can be repeated. Abby received the code 1234. We want to know what the probability that she would receive a code of consecutive numbers. So let's think about this. When you say you've got a 4-digit code, there are 10 digits, 0 through 9, and we want to choose 4 out of the 10. So that sounds to me like we've got a permutation. Order isn't important. The permutation of 10 choose 4, which is 10 factorial over 10 minus 4 factorial. So 10 minus 4 factorial would give us 6 factorial. And 10 factorial, we could write that reduced down till we got to 6 factorial, which would take care of the denominator, and the 6 factorial in the numerator. 10 times 9 times 8 times 7 is 5,040 different ways we could have a 4-digit code out of the 10 digits. And we want to find the number of favorable outcomes. So let's say that we write those down. I would recommend you turn off the video and see how many you can find. And it seems like I found 14 consecutive 4-digit codes. So if we want to find the probability of getting consecutive codes then that would be 14 for our favorable outcome out of a total of 5,040 possibilities, and that becomes 1 in 360. In example 6, we have 6 books that are labeled A through F, and they're arranged at random on a shelf. We want to know what the probability would be if they were arranged in alphabetical order. So the probability would be a permutation of 6 books chosen 5 at a time. So 6 times 5 times 4 times 3 times 2 times 1 divided by 6 minus 5 quantity factorial. So we have 1 factorial in the numerator divided by 1 factorial in the denominator, and that is 720. So the probability would be 1 in 720 chances. The probability, 1 in 720. The probability that they were lined up alphabetically, A through F. Let's erase this here. That they were lined up A through F would be 1 time out of the 720. And then in example 7, we're looking at a 4-card hand is to be picked from a deck of 52 cards. What's the probability that the cards will be face cards? So the face cards in a deck of cards are the Jack, Queen, and King. So we have Jack, Queen, King. And in any deck of cards, there's 4 suits, which are diamonds, hearts, clubs, and spades. There's, out of 4 suits with 3 face cards, there are 12 face cards in all. So I got to think through a deck of cards. And we want the probability, so I want that they'll be face cards. The combination of 12, choose 4, and the combination of 52, choose 4. So there are, using my calculator here for this calculation, combination of 12 cards chosen from or 4 cards chosen 12 at a time. That's 495. And 52 choose 4 is 270,725. And you can reduce that down to 99 out of 54,145. And if you find the percentage, that's not even 1%. So your probability is not very good. Example 8, there's 12 balls in a box, 3 each of red, green, yellow, and blue. You're going to take 3 balls chosen at random, and we want to find the probability that all 3 of the balls are green. In this case, we can calculate that with just simple probability. Order isn't important, so the probability that we're going to get 3 green balls out of the box would be, first you got the first draw, that's 3 out of 12. And then if you got the green ball, then you would have 2 green balls left out of the 11 total. And if you got the second green ball, then you would have 1 green ball left out of the 10 remaining. And reducing those fractions, 3/12 is 1/4, and 2 divides 10 5 times. So we got 1/4 times 1/11 times 1/5. 4 times 11 times 5 is 220. So you have a 1 in 220 chance of grabbing the 3 green balls out of the box with 12 balls total. Moving on to our example with geometric probability. Geometric probability is a form of theoretical probability That's determined by a ratio of lengths, areas, or volumes. And in example 9, we have a dartboard. This is our dartboard up here. And suppose that all the points are equally likely to be hit by a dart you throw. Could you find the probability of scoring at least 10 points? So if I'm scoring at least 10 points, I would want to score in this blue area here or this peach area. So there's 2 areas, and it looks like each little ring width is 2 inches. So in that case, we know the area of a circle is pi r squared, so we're using this idea of a ratio of areas. And if the area is 2r, then that would be 4 pi r squared. And if the area was 4r, that area would be 16 pi r squared. So we want to score at least 10 points, which would tell me that I want the probability of at least 10, so some score greater than 10 or equal to 10 would be the area of the 2r. So if I just got the 10, that would be 4 pi r squared divided by the larger area, 16 pi r squared, which is 1/4 or 25%. Then the probability of scoring 20 points would be pi r squared divided by 16 pi r squared, which is 1 out of 16 or 6.25%. And then part C, the probability of scoring 5 points. Let's look at it again. So 5 points would be the 2 and the 5. So let's see. Think this through. So there's 3 rings. We got 3 that we don't want. So pi times 3r squared. And then the one that we do want is pi times 2r squared over the whole thing, which is pi times 4r quantity squared. So that looks like 9 pi r squared minus 4 pi r squared divided by 16 pi r squared. So we've got 5 pi r squared divided by 16 pi r squared. Our pi r squareds can cancel. So 5 out of 16 or 31.25% of the time you would score 5 points. For example 10, we have a baseball player that got a hit 21 times in 60 at-bats. We want to find the probability of him getting a hit. So he was at bat 60 times. The probability that he got a hit is the 21 times out of 60, which is 21 divided by 60 is 0.35, or we could say 35% of the time he got a hit. And then our last example, your class rolled a die and recorded their results shown in the table below. What is the experimental probability of rolling each number? So to roll a 1, well, first we need to add these up: 43, 45, 41, 46, 48, and 47. That's a total of 270 rolls on the die. So to roll the number 1 would be 43 out of 270, and that's roughly 15.9% to roll the number 1. To roll the number 2 Number 2 is 45 out of 270, which is 1/6 of the time, or about 16.7%. Rolling a 3, we got 41 out of 270. To roll a number 3, 41 out of 270, and that's roughly 15.2%. So you can see they're all really close to the same percentage on a fair die. To roll the number 4, this is 46 out of 270. So we're looking at experimental probability. That's 23 out of 135, and that's roughly 17%. And then 2 more. To roll the number 5 was 48. So 48 times out of 270. That reduces to 8 out of 45, or about 17.8%. And last but not least, to roll the number 6, you got 47 out of 270, and that's about 17.4%. So on a fair die, anywhere from 15 to 17%. That's the end of our lesson 2. See you next time.